Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. I was discussing about Unit 3, different topics which were covered in Unit 3. First was electrochemistry, then corrosion, and now coming to the next part, that is the phase rule. Now, for an heterogeneous system, phase rule is an important tool for predicting the number of phases between which the equilibrium is going to exist. Then, till what temperature and pressure these phases are going to be in equilibrium, and at what temperature and pressure one of these phases would disappear and or they are going to get interconverted into each other, or they are going to meet at a certain point. So, for studying equilibrium between different phases, this phase rule is a versatile tool. Now, according to the phase rule, it says that the degree of freedom can be predicted by knowing the number of phases between which the equilibrium exists, and also by knowing the chemical composition of the different compounds which are taking part in the equilibrium or which are present at the time of the equilibrium. Now, this phase rule, it was given by Willard Gibbs, and it states that when the equilibrium between any number of phases is influenced only by temperature, pressure and concentration, that means these are the variables, but it is not influenced by gravity or electrical or magnetic forces or by surface action, only then it is given by a mathematical equation that capital F, which stands for degree of freedom, is given by number of components capital C minus number of phases capital P plus 2. This 2 accounts for the changes in temperature and pressure. Now, the phase rule, it is defined as the number of degrees of freedom exceeds the difference of the number of components and the number of phases by 2. Now, according to this equation, if there are more number of phases which are in equilibrium, then the degree of freedom will reduce. That means the chances of variation or in temperature and pressure will reduce, otherwise the equilibrium is going to get disturbed. And if the value of components, different chemical compositions, if the value of components is high, then the degree of freedom is also going to be high. That means we can vary temperature or pressure, or temperature and pressure both can be varied. So, coming to the different headings which were discussed in phase rule. Phase rule, here capital P stands for number of phases. So, what exactly do we mean by phase? Now, phase, it is physically distinct. For example, we have two phases, a solid and a liquid, so they are physically distinct, we can separate out them, and they are mechanically separable part of a system which is separated by other parts of the system by real or imaginary boundaries. For example, if we have a sugar solution, and this sugar solution, it contains high amount of sugar, so that the sugar is settled at the bottom of the glass. So, we can see settled solid sugar at the base of the glass and a sugar solution which is above. So, there are two phases, one is a solid phase and another one is a liquid phase, and they have a boundary between the two. The solution is separated by the sugar, solid sugar, by a boundary. So, now these phases, They can be of three types: solid, liquid or gaseous. So first I am discussing about a gaseous phase. A gaseous phase, all gases are completely miscible and they have no boundaries between them. If all the gases we are talking about, they are miscible with each other, then they have no boundaries between them. Hence, all gases constitute a single phase. For example, air. Air is a mixture of oxygen, hydrogen, nitrogen, carbon dioxide, and even water vapor is present. So, that air, it constitutes a single phase. A solid phase, every solid constitutes a different or a separate phase. For example, if I consider an example of decomposition of calcium carbonate, here calcium carbonate dissociates to give calcium oxide solid plus CO2 gases. So, gas is a separate phase, but since the chemical composition of calcium carbonate and calcium oxide is also different here, so these two solids, they are going to show a different phase. That means in this example we have three different phases because we can separate calcium oxide from calcium carbonate. So, third, a water system has three phases, namely a solid phase, a liquid phase and a gaseous phase. Ice, which is the solid form, then water, which is the liquid form, and water vapor, which is the gaseous form. So, here solid, liquid and gaseous, all three different phases are present. Therefore, the number of phases is going to be 3. Then next is the solution of a substance in a solvent. It constitutes one phase. Now, when we dissolve a solid in a solvent, after the solute or the solid, it completely dissolves in the solvent or the liquid, then in that case they constitute a single phase. For example, sugar solution in water, or for that matter salt solution in water, or the lemonade that we make. Here again the lemonade completely mixes with water, again it is going to constitute a single phase. But here if I talk about the saturated solution, saturated sugar or salt solution, then again the solid sugar will be resting at this solid sugar, it will be resting at this solid sugar will be resting at the base of the glass, and here is going to be the solution. So, we can clearly see the two different phases which are going to be present in the saturated solution. Now, here the number of phases is going to increase. It is going to increase from one phase to the two phases. So, unsaturated solution, it is constitutes of a single phase, but saturated solution, it constitutes two phases. Next, I will be talking about components. What do we mean by the components in phase rule? The number of components in a system, it is the maximum number of independently variable chemical species necessary to describe the composition of each phase. So, it is the different chemical compositions of any species which are present at the time of the equilibrium. For example, if I talk about water system, now in the case of water system, I was talking about three phases: ice, solid, water, liquid and water vapor. So, here we are talking about the three phases: ice, solid, water, liquid and water vapor. Though they are three different phases, but the chemical composition of all the three phases is going to be H2O. So, the chemical composition will remain same and it is H2O. So, the chemical composition will be of all the three phase is H2O. Therefore, the system is one component system. Now, similarly, sulfur, it exists in 4 different phases: sulfur rhombic, sulfur monoclinic, liquid sulfur and vapor. Though the number of phases are 4, but the chemical composition of all the 4 phases is only sulfur. Only S is present in all the 4 different phases. So, here again the number of components is going to be 1. Next is the thermal decomposition of calcium carbonate. If I talk about decomposition of calcium carbonate, now this calcium carbonate solid, it dissociates to form calcium oxide solid plus CO2 gas. So, here if I am talking about the chemical composition, so the number of components is the minimum number of chemical compositions which are necessary so that we can express the entire equilibrium. Out of these 3, what is the minimum number of chemical composition that I need to know so that I can write this equilibrium? Here, if I say in terms of calcium carbonate, if I do not know these 2, then in terms of calcium carbonate, I will always know that the calcium carbonate will dissociate always into calcium oxide and CO2. So, on viewing only calcium carbonate, I can say that it is one component system. But if it is one component system, then by knowing any one component, any one of these chemical compositions, I should be able to write the complete equilibrium. But here if you see that if I do not know the other species which are present in the equilibrium, if I know only calcium oxide, then by knowing only calcium oxide, can I write the entire equilibrium between the different phases? Can I write the chemical composition of calcium carbonate or that of the carbon dioxide? No. Similarly, if I know in the equilibrium only carbon dioxide, can I write the other 2 chemical compositions? No. That means this system is not one component system. For being one component system, then I should be able to express this equilibrium by knowing only a single chemical composition of any one. So, it is not one component system. Then I move towards the higher component system, that is the 2 component system. So, if I know the chemical compositions of 2 out of these 3, then can I express this equilibrium? Suppose I know calcium carbonate and calcium oxide, then calcium carbonate minus calcium oxide will always give me CO2. Similarly, if I know calcium carbonate and CO2, then calcium carbonate minus CO2 will always give me calcium oxide. And if I know that calcium oxide and CO2 are present in the equilibrium, then calcium oxide and carbon dioxide, they are going to mix together or react together to form the calcium carbonate. That means I should know minimum chemical compositions of at least 2 phases. Only then I can express this equilibrium. So, here in the thermal decomposition of calcium carbonate, it has 2 components, as the composition of each of the above phases can be expressed as equations considering any 2 of the 3 components present. When calcium carbonate and calcium oxide are considered as components, so the chemical equations, they are given as calcium carbonate phase can be described as calcium carbonate plus 0 calcium oxide. Similarly, we can describe the calcium oxide phase by using 0 calcium carbonate and calcium oxide, and CO2, it can be this phase can be described by using calcium carbonate minus calcium oxide. Similarly, while studying the dissociation of ammonium chloride, now by considering the dissociation of ammonium chloride dissociates to give ammonia gas as well as hydrochloric gas HCl. Now here this system consists of two phases, which is the solid NH4Cl, which dissociates to form NH3 and HCl. Now if the partial pressures of NH3 and HCl they are equal, or if these NH3 and HCl they are present in equivalent quantities. I am talking about the closed systems. When the system is closed, it is not in contact with the environment. Either the partial pressures of both are equal or they both are present in the equivalent quantities. Then the composition of both of these phases, NH3 and HCl, it can be expressed by NH4Cl only, because NH3 and HCl will react and they will form ammonium chloride. No extra NH3 or HCl is going to be present in the system. So here in this case, when they are present in the equivalent quantities, the system will be one component system. But if the partial pressures of NH3 and HCl they are not equal, that means they are not present in the equivalent quantities, then suppose ammonia is present in excess. So equivalent amount of ammonia will react with HCl to form NH4Cl, but the excess amount of ammonia, it is going to remain in the system. So in the system we are going to have NH4Cl, but we are also going to have ammonia. That means, and the chemical composition of ammonium chloride and ammonia are different. So in that case, the number of components is going to increase and the number of components will then become 2. Next, coming to the degree of freedom. What do I mean to say by degree of freedom? Now here the degree of freedom is the minimum number of independently variable factors. Independently variable factors that can be varied during the system for maintaining the equilibrium, like temperature, like pressure, like composition, which ought to be fixed, in order to represent the condition of a system. It is known as the degree of freedom. So, which is out of these three, temperature, pressure and composition, the minimum number of these variable factors which must be fixed to represent the condition of the system, to represent that equilibrium, it is known as the degree of freedom. Now degree of freedom can vary, it can be 0, it can be 1, it can be 2. For 0, the system is going to be non-variant, that means we cannot vary the temperature or the pressure. For degree of freedom 1, we can either vary the temperature or the pressure, we cannot vary both of them. But for bivariant system, we can vary. If the degree of freedom is 2, it is called bivariant, that means we can vary temperature and pressure both. And if the number of components are more, then the system can also be trivariant, that means we can vary temperature, pressure and composition of the system. For example, I am going to consider the following equilibrium. Here ice solid is in equilibrium with water liquid, which is again in equilibrium with water gas, vapor gas. So here the three phases are in equilibrium. The three phases are in equilibrium and number of component is 1, because the chemical composition of all these three phases is only H2O. So these three phases, they are going to be in equilibrium at a particular temperature and pressure. You cannot vary the temperature or the pressure. That means the degree of freedom is 0, and hence the system is non-variant or zero variant or invariant system. Now suppose I consider the equilibrium between only liquid water and water vapor. So since only two phases are in equilibrium, the degree of freedom becomes 1. The degree of freedom according to equation F plus P is equal to C plus 2, because this is one component system. So degree of freedom becomes 1. That means we can either vary the temperature or the pressure. We can vary any one of them, or one can be varied and other has to be fixed to describe the system. So in this case the degree of freedom is 1. Now coming to the applications of phase rule. Now this phase rule, it helps in understanding the properties of materials such as metals or alloys and composites. Then it is used in different metallurgical processes. It is also used in solvent extraction and distillation. It is used in the quality control of ultra pure materials like semiconductors, and it is used to check impurity concentration. Now this phase rule, it is applicable to macroscopic systems, the larger systems, and this phase rule predicts at what temperature and pressure which phase is going to exist of a substance, and at what temperature and pressure, if we change the temperature and pressure, does the two phases are going to interconverge into one phase. That means one phase will move out of the system and they are going to form a single phase system, and at different pressure and temperature how different phases are going to show their existence. Now coming to one component system, here I am going to discuss the water system. Now this water system, it is a typical example of one component system. Water system, water exists in three different phases: ice, water and water vapor. So since three different phases are there and there is an equilibrium between the three phases, ice is going to be in equilibrium with water. Similarly, ice will also be in equilibrium with water vapor, and water will be in equilibrium with water vapor. And the phase diagram I am going to show, it is going to show different curves, the areas and triple point. Now this phase rule, we can describe the different phases by Clausius-Clapeyron equation. It says that the variation of pressure with temperature, on varying the pressure with temperature, there is a variation in entropy and volume. So on changing from solid to liquid, entropy, randomness increases as well as the volume generally, and similarly on changing from liquid to vapor, again entropy is going to increase and similarly the volume will also increase. So according to this equation, on change of pressure with temperature, there is change in entropy as well as change in volume. Now here I am showing the water system. This is the phase diagram of water system. This is the temperature in degree centigrade. This is the pressure in atmospheres. Now since water exists in three different phases, we can see that water, it is existing in the ice, water liquid and water vapor state. Now, as I was discussing this, if I see a normal temperature pressure diagram, then generally for all the substances, on increasing the temperature, the pressure also increases. General diagram, phase diagram is going to be this, but in the case of water, the phase diagram is this. The phase diagram is going to be in this way. That means this curve, ice melts with a decrease in volume. This curve is between ice and water and it has a negative slope, but in all other substances, all these curves are going to have positive slope. If I increase the temperature, pressure increases, but here on increasing the pressure, the temperature drops. On increasing the pressure, the temperature drops because ice melts with a decrease in volume. So here, coming back to the diagram, this area BOC, it represents ice solid. Area AOC represents water liquid, and area BOA, this area, it represents water in the vapor state. So these are the different areas which represent ice in different forms. So coming first only to the areas, if I study these areas, then in this area ice is a stable form, in this area water is stable, and here water vapor will be stable phase. So according to the equation, F plus P is equal to C plus 2. So number of phase in these areas is only 1 and the component is one component system I am talking about. So degree of freedom will become 3 minus 1, which comes out to be 2. So in the case of areas only, the degree of freedom is going to be 2. That means we can independently vary pressure as well as temperature. Even though on varying, these phase will not disappear. Now coming to the different curves shown in this diagram, phase diagram. So first, this OB is the sublimation curve of ice. This OB, it shows ice and water vapor in equilibrium, and this is the sublimation curve of ice. Above this line OB, ice is a stable state, and below this line OB, water vapor is the stable phase, and on this line OB, ice will coexist with water vapor, or you can say on this curve, ice is in equilibrium with water vapor. And this curve, it extends to the absolute zero of temperature. Similarly, coming to this curve OA, this curve OA is the vaporization curve. It is the vaporization curve, and above this curve OA, water is a stable state, and below this curve OA, water vapor is the stable state. And on the curve OA, both water liquid and water vapor are going to coexist with each other. So here, water at any given temperature is associated with vapor. With the increase in temperature, there is increase in vapor and vapor pressure. The rate of increase is higher at higher temperature than at lower temperature. So on this case, you can say that pressure, it becomes dependent on temperature. If I fix the temperature, then the pressure will automatically be fixed. So, here the degree of freedom is only 1. I can vary either temperature or pressure. And this curve OA, it extends up to the critical point. Critical point, in this case, critical temperature is 374 degrees centigrade and critical pressure is 218 atmospheric pressure. So, beyond this point, only water exists. Beyond this critical point A, only water is going to exist and vapor is incompressible beyond A, and it gives rise to supercritical fluids. Supercritical fluids are also utilized in different studies. So, it gives rise to a heavier or a denser liquid which is known as the supercritical fluid. And the point O, it is the lower part of the vaporization curve which represents the freezing point of water. And this freezing point of water, because beyond this point O, water will not show its existence, and the temperature and pressure corresponding to this point O, they are 0.0098 degrees centigrade and 0.006 atmospheric pressure at point O. Thank you.